Okay, everybody, I want to take you through the first introduction of this lab. So make sure you're reading all the bits and pieces of the lab. At the very beginning, it's reviewing a little bit of what we've talked about before, that we know that a function is increasing when the derivative is positive, and the function's decreasing when the first derivative is negative. But we also then are going to go down to, and we've discussed this a little bit before, about concavity. So remember, the second derivative is the slope of the slopes. And if we think back to what we had talked about before, in a graph that is concave up means basically that the slopes are increasing. I'm going from negative slopes to zero slopes to a positive slope. Those slopes are increasing. So the rate at which the slopes are changing is increasing. So it's the slope of the slopes, or the second derivative. So the second derivative tells me about concavity. And obviously that would be for concave down. So a function is concave up when the second derivative is positive, and the function's concave down when the second derivative is negative. So what I want you to do is to take your latest foldable, and what I want you to do is to flip it over onto the back, where there's a lot of big blank space, and then maybe turn your foldable sideways. I want to make a little table here. This is going to be F prime, and F double prime. And I'm going to have 4 different columns here to show some relationships. And again, you can pause me at any point in time, but I'm basically going to summarize what's discussed here because we haven't discussed the relationship between F prime and F double prime. I'll show that connection here in a second, all in an effort to sketch a curve. That's everything that we're going to do. So let's make this table first. So I can then tell whether or not, if the first derivative is positive or negative, what's happening with the original function. If the original function is increasing, or physically from the graphs, if the position or the sign, positive or negative, if I have a first derivative that has a positive position or it's above the x-axis, that means then the original function is increasing. And that's then telling me the slope of the original function. So the slope of the original function, whether or not it's positive or negative, will tell you the position or the sign of the first derivative and vice versa. Well, that's one derivative away. So the same relationship would happen for the first and the second derivative. That the slope of the first derivative, that graph, the first derivative graph, is going to tell you the position or the sign, positive or negative. And by position, I mean relative to the horizontal axis, above or below the horizontal axis, or the sign of the first or the second derivative. So again, the first derivative and the second derivative have the same relationship as does the original function and the first derivative. And that's what this is showing right here. These two are the same. It's just that function first derivative, second derivative. It's one derivative away. But when I go from the function to the second derivative, that's talking about concavity. So the concavity of the original function f can be determined by the position or the signs, positive and negative, of the second derivative. The second derivative is positive, I'm concave up. Second derivative is negative, I'm concave down. So there's a lot of the relationships between my 3 different function graphs. And yeah, if you want to think of this about position, velocity, and acceleration, absolutely. We could look at those as well. But there is one more relationship here, and maybe see if you can figure it out, that the packet I don't think discusses. It's the relationship between the original function and the first derivative. Besides being the slope and the position, there is a way for me to tell the concavity of the original function, but from the first derivative graph. Well, how can I do that? Concavity came from the second derivative, which was based upon its position, but the position of the second derivative also comes from the slope of the original or the first derivative. So the slope of the first derivative will tell me also the concavity of the original function. If the first derivative has a positive slope, the original function is concave up. If the first derivative has a positive slope, that means the second derivative is positive or above the x-axis. which then means the original function's concave up. And again, also for negatives as well, concave down. So this is a nice little handy chart to kind of keep track of things when we're going through in the lab and anytime that we're trying to discuss or look at graph behavior. So what I want to do is I want to go to the next part in the lab. The next part in the lab says, find a sign chart for the first and second derivatives. Determine where the function's increasing and decreasing. This is what we've been talking about here recently. Turning points, maxes and mins, and then the extremums. And the same thing then for the first derivative in terms of where is it concave up, concave down for the original function. So I'm going to go through and I'm going to take this first function and model it for us here. So my function is negative x cubed plus 3x minus 2. So I'm basically going to go through what I want to see here in part A. You can then do part B as you're working through the lab. All right, so I'm going to break my paper kind of in half here. And I'm going to then here find the first derivative. So negative 3x squared plus 3. And I want to find all the critical points. Well, the critical points are where the derivative equals 0 or where the derivative is undefined. Let me get this refocused here. Give me a second. All right, so I'm going to set the first derivative equal to 0, which means I think I can factor out a 3. So x squared minus 1. And so if I set x squared minus 1 equals 0, setting negative 3 equal to 0 is not going to give me any solutions. So I get plus or minus 1 when I take the square root of 1. So I want to make a sign chart, which is a little number line. And I'm going to label this as f prime. And I've got two critical points, negative 1 and 1. And the first derivative for both is 0. So the first derivative is 0 for both of those. Now I'm going to test some points within these little intervals. So back here, negative 2. What would the first derivative be at negative 2? Well, if I go, you can either put it into the original first derivative or the factored form. I like the factored form. Negative 2 squared minus 1, well, that's positive. This times negative 3 will make this negative. Easy number in here is 0. Negative 3 times, so 0, that's a negative. So a negative times a negative, that's going to be a positive in here. And something like 2 squared minus 1, that's positive. That's negative, so it's negative. And again, we know that there's going to be no other signs within these intervals because in order for these signs to change, I would have to pass through 0, and I've already found all my critical points. So what does this mean about f? Underneath, I'd like us to write f. And if the first derivative is negative, if the sign of the first derivative is negative, what does that tell me about the original function? Well, the original function must have a negative slope, so therefore the original function must be decreasing. And then increasing on that interval and decreasing on that interval. So that's telling me my intervals. I'm good with that. So therefore, what's my conclusion? What's happening at negative 1? Well, at x equals negative 1, well, what do I have? I have a graph that's going from decreasing to a 0 slope to increasing. Decreasing, 0 slope to increasing, that sounds like a local min. And what's happening at my other critical point at 1? Well, the graph's going from increasing to a 0 slope to decreasing. So that sounds like a local max. Now, I can actually get those coordinates by going to the original function. So I'm going to take negative 1 and substitute it into the original function. I'll save us a little bit of time here. That's negative 4. I'm going to take 1 and put it into the original function. If I put 1 into the original function, I wind up getting 0. So I actually know the coordinates of the local max and min. And notice we use the graph's behavior around them, not substituting in points into the original function like we were earlier. All right, so maybe if I then start down here to maybe plot some points. Again, my whole concept here is to get a good description of the or graph of that function. So negative 1, negative 4, that's going to be a local min, and 1, 0, that's going to be a local max. Well, now I need to, and I know the behavior in between. I know I'm going to be decreasing, increasing, and then decreasing. Now let's check what's going on with the concavity, which means I got to take the second derivative. So negative 6x. Find its critical points by setting it equal to 0. It looks like I get one easy critical point, which is just 0. Now I'm going to make a second derivative number line. So at x equals 0, what is the second derivative? Well, at x equals 0, it was 0. Now let's test some points on either side. What about if I put a negative number into the derivative? Well, I'm going to get a positive. And if I put a positive number into the second derivative, I'm going to get a negative. So what's that tell me about f? Now, I could find some information about f prime, but my goal really is to get a graph of f. So what's that telling me about f? Well, if the second derivative has a negative sign, then that means the original function must be concave up, if this is positive. So this is concave up and concave down. So what does that mean? That means at x equals 0, I have a place where the concavity changed. And what does that represent? That represents a point of inflection. And I can get its actual coordinate by going back to the original function, putting in 0 into the original function, and you can see I get negative 2. So I'm going to go to 0, negative 2 right there. Now, if I didn't know anything about the graph's behavior, look what I've got on my graph. This looks like it's almost linear, but I've got a lot of information up above to fill me in. Okay, so prior to negative 1, what do I have? I have the graph is going to be decreasing, and prior to negative 1, it's going to be concave up. So I'm going to be decreasing and concave up, heading towards a 0 slope right there at negative 1. Now, after negative 1, I'm going to start to increase, but I'm still going to be concave up until I get to 0. So I'm going to be concave up here. So I have, remember, concave up is increasing slopes. But now once I get to 0, negative 2, now I'm going to be concave down, but I'm still increasing. I'm going to keep increasing until I get to 1. But now I'm going to be concave down. So increasing concave down, remember another definition for concavity is that the tangent lines would lie above. And then once I've reached 1, now the function's going to start to decrease, but still be concave down. And then head down here. So not only with my critical points, can I plot the points, but then I can describe the behavior in between. This is a perfect example of what I'd like to see for both A, and then you're going to do B as well in this section. But then what the next part does is it doesn't give you the equations, it actually gives you the sign charts. So underneath, you want to be then filling in information about F, taking any additional information that they give you. In this case, they give you a little point to plot, and then using that to sketch the curve. So again, these don't give you the functions, they're actually giving you the sign charts, and then you go and sketch the curve. All right, so continue with going through those problems as your introduction to this lab.